Hello, good morning, guys. My name is Alexa Melendez. I am part of Group 3, and this is Physics Force News, Lab number 4. So, as you can see, we are going to be comparing snapshots of the graphs from last week and this previous week. As you can see, the one on the left is going to be the one from last week, and the one on the right is going to be the one for this current lab. You can see clear cycles of the objects rising and falling, which gives us a much better look at how energy is actually moving throughout the system. Um, Last week, for this image, it's going to be the top two tables. It's going to be the ones from last week. So table 1, the theoretical acceleration that we got, and then the one for table number 2 is going to be based on the values for the initial and final velocity. And for the last image, which is going to be at the very bottom, is going to be table number 1 for lab number 4, which is going to be pretty much comparing the acceleration, the hanging mass, the glide's mass. So as you can see, acceleration for last week we had 1.128 meters per second. For this week it was 0.480 meters per second. So it does affect it because we had to add more weight for our glide. So last week I believe it was 25.5 what we had. And this week it was a bit more heavy since we did have to add 10 and 10 grams to the side, which changed the velocity and made it slower. So we can see that it ran a linear fit of the velocity. So the slope was 0.972 meters per second, which is important because there is consistency. So when the velocity hits 0 on the line, you can see how it matches up perfectly at the very top for the position arcs. This last slide is going to be based on the table that is going to be basically showing a clear comparison of last week and this new week and the trend. So the glider mass was increased by 20 grams, which is last week was 25.5 grams, this week was 45.5 grams. So that tells us that it increased for the glider mass and the acceleration was decreased. As you can see, last week we had 1.128 meters per second, and this week it was for 0.480 meters per second. That's all I have for you guys. Thank you so much. You guys have a good day.
I'm Jeremiah Olguin, and following Alexa's report on the initial setup, I took the lead on our theoretical projection for Table 2. To test the limits of Newton's second law, our team decided to decrease the system's acceleration by significantly increasing the glider's mass. Starting with the reference values from last week. An old theoretical acceleration of 1.128 meters per second squared, we adjusted our variables by increasing the glider's mass to 45.5 grams, while keeping the hanging mass consistent at 3.31 grams. Our new theoretical acceleration dropped to 0.480 meters per second squared. Using the percent difference formula, where the old acceleration serves as our reference value, we calculated a planned theoretical difference of 57.45%. This represents the significant change we expected to see in a frictionless environment before we started our trial. Now, I'll hand it over to Jade, who will break down the table 3 velocity values to see if our experiment runs match the absolute projection. This has been Jeremiah, and thank you so much.
In this part, we calculated the percent difference to understand how much the acceleration changed in our experiment. Sorry. First, we use a formula that compares an old value with a new value. This formula help us see the percentage of change between the two results. We follow three simple steps. First, we subtract the new acceleration from the old acceleration to see how much it's decreased. Second, we divide that change by the original value to understand how big the change was compared to the starting point. And third, we multiply the number by 100 to turn into a percentage. And to the end, we found that the acceleration decreased by a little more than half. Everyone, I'm Christian Perales, reporting live from the live tonight. Our investigative team is putting Newton's second law to the ultimate test. We want to see if the theoretical physics found in textbooks can survive in fraction of a real world environment. To conduct this investigation, we utilized a precision air track and a glider with a mass of 196 grams. To get the glider moving, we use a hanging weight of 26 grams, which it provides the constant pulling force needed to drive the system. Monitoring the glider's every move was our high frequency motion sensor. This sensor tracks the glider's position in real time, feeding the route data directly into the capstone software. This allows to translate physical movement and the digital graphs you are about to see. Thank you.